Till now we have been using the classical approach to design controllers. Let us now move towards the state space approach. You see here the two equations, the state equations. They are all vectors, matrices. This first one is the next state equation, where x is the state variable, a and b are the parameter matrices. A is the system parametric matrix and b is the input matrix. The second equation, yk, which is equal to cxk plus duk, is the output equation. Again, c and d are the output parameter matrices. Though we have discussed the state space modeling in an earlier lecture in this series, let me just very briefly review what it means and what it is before we look at the state space approach to controller design. So this is the plant to be controlled. You have the 4 ports, the generic ports, the power input port, the control output port, control input port, and the sense port. Generally, this plant was represented in the classical domain using the transfer function. And we saw how to design the controller using transfer function by the root locus method. But note that in the classical notions of control, which uses the frequency domain parameters and S-plane parameters, there are some disadvantages. It can be used only for single input, single output systems. It can be used only for linear time invariant systems. And also in the case of the transfer functions, by definition, you assume that the initial conditions are 0. All these problems are alleviated when you use the state space approach. It's a much more powerful way of modeling the system, and not only that, and even for designing the controller, as you will see by and by. So let us represent this plant with the parameter matrices of the state equation A, B, C, D, A, B, C, D, and we interconnect it like this equation, like the state equation. So when we interconnect, so you see here the next state equation is of this form. So you have the U control input coming in through scaled by B, BUK, and you have the state scaled by A, you have XUK added. If you add these two, sum them up, at this point it is the next state value XK plus 1. Delay it further, you get XK. C and D are the output equation parameter matrices. And D, of course, is the direct feed through matrix. In most of the cases, there will not be direct feed through, and such cases D will be 0. And the output equation will only be y is equal to cx. So if you take an example of a 2-state system, you have a state variable having only 2 elements. So let's say the state equation, the next state equation looks like this. X is a vector which is having 2 elements, x1 and x2, so column vector, k plus 1, and xk, the same 2 elements, same 2 state variables at kth instant, and uk. These 2 blank matrices I am showing here are just placeholder matrices for the values of the parameter, system parameters. A vector will come, A matrix will come in here, and the B matrix will come in here. Likewise, for the output equation, yk, you have this state vector xk, and C is in this case a row vector, C1 and C2, 2 elements, and D is you could have a D matrix like this, or you could probably have D0 if there is no direct feed through from the input to the output. So this is probably how the state equations will look like for a two-state system. So like that you can probably visualize it for n-state system. Let us now recall the small signal control in the context of state space approach. So this here is the plant to be controlled. This is a simple buck converter circuit or a step down converter circuit. The switch here, the semiconductor switch MOSFET, is being controlled. So that is the input U. So I am using the same symbol U for the control input, Y for the controlled output, and that is also being sensed, and we will feedback that. Now here I am going to draw this X and Y axis. The X axis is U, control input, Y axis is Y, which is the controlled output. So let us say that it is of some arbitrary shape like this, the curve, and we have an operating point. So in the neighborhood of the operating point, we would like to see the deviations. So let's say the operating point is this uppercase U. This is the input that is applied, and this is the nominal output that is obtained. And our interest is to see that in the neighborhood of the operating point, the deviations. So if there are deviations, will the control system be able to take control and bring it back to the operating point? So you have this deviations, delta U and the delta Y. So what is that relationship? So this will follow the Taylor series, and this is the Taylor series. And delta U and delta Y being very small, we can take only the first order term here. So let us take this first order term. So this will be delta Y, which is if I consider in the neighborhood of the operating point it to be linear, so it will be a constant rate into delta U. So we have this kind of a linear system. This is called linearization, small signal linearization, which is done for every system so that the controller is not overstressed. So if you consider such a linear control system like that, so let us say we feedback the sensed output and place the various blocks, the control blocks, in perspective. So you have the sensed output Y, then you have the controller, the error goes through the controller and as control input here. Finally, the output of the controller goes as a control input. Now here this Y, what you are sensing is comprising two parts, the operating point Y and the deviations in the neighborhood of the operating point Y, or the nominal Y. So that is this lowercase y that we have written, and the reference will be the operating point Y, the uppercase Y. So there is an error, which means that the error is the deviation in the neighborhood of the operating point, that is delta Y minus delta Y, that passes through the controller and results in the control input. So this is what the normal controllers will do. But when you do a feed forward control, you would like to give a feed forward component. So where the moment I know that there is a reference point Y, I know what will be the reference point input that I need to give based on the model of the system, and I can give the reference point input U. So if you give U, the controller needs to deal with only delta U. So the controller, the relationship between delta U and delta Y we saw is more or less linear, and therefore this will be a linear gain K. So this delta U and delta uppercase U, which is the operating point U, combine together to form U as the control input. So this is basically the setup that we would use even in the state space approach, and this is called the small signal controller. Now let us look at few other components that will go on to make the complete controller. How do we get this reference and how do we get this feed forward part? In this specific example, we see that here we are feeding back the output voltage. In this case, it is the output Y. Controlled output Y is nothing but the output voltage, and we are feeding back the output voltage, and probably you will have to give a voltage reference. The controller will detect the error and give an input, control input accordingly. And the control input here in this case is the switching on and off of this device, this semiconductor device, which is the duty cycle. But in a more generic case, we say that whenever the output, controlled output is being fed back and the control input delta U is proportional to the feedback output, then we say that it is an output feedback control. Just because the name says it all. It is an output feedback output, that is controlled output, that is fed back. It is called output feedback control. So likewise, if we feed back all the state variable information, so let us say we have the inductor current. Inductor current is also a state variable. So let's say we feed back that. The capacitor voltage is state variable. We feed back that. So which we are anyway doing. The output voltage is directly the capacitor voltage. So that is one variable we have, the information, the current information through the inductor. If you include that also into the feedback, then you are feeding back the entire state vector. So in such a case, it is called state feedback system or full state feedback system. The input, the deviation input, will be proportional to not delta Y but delta X, deviation of the entire state vector. Such a system is called a full state feedback system. Full state feedback system has several advantages over the traditional feedback control, that is the classical method of feedback control, which we shall see and also design. Let me now consider a three-pole system, three open loop pole system, and let us see how we place the poles of the closed loop system. Now consider the Z plane, and let me mark the unit circle on the Z plane, and let us place the three open loop poles along with the root loci. So this is pole 1, open loop pole within the unit circle and its root locus. This is the other complex conjugate pole, second pole, and its root locus. Then there is the third pole I'm going to place here and the root locus along the -x direction. Now the closed loop poles lie where? They lie on the loci of the root locus. So any of the points on the root loci are closed loop pole locations. So we choose the most appropriate or the pole locations which give the best step response. So that is how we do the root locus design, right? That's how we have seen that. We do that. So here place the poles on the root loci within the unit circle, but the point is that we place it on the root loci. Compare this with the state feedback method. What is it? The preview is like this. You have the Z plane and you have the unit circle, and the advantage here in the state feedback method is for the same three open loop pole system, you can place the closed loop pole anywhere within the unit circle. In fact, that is the most powerful advantage that you would get with the state feedback method. Place the poles, closed loop poles, anywhere within the unit circle for any given open loop pole locations within the unit circle. So this is the power of this full state feedback method. Let us now discuss pole placement by full state feedback. For any given plant, you see a plant here which is having a power input and a controlled output, and there is a control input. So generally we talk of a control law, which is actually the relationship of this control input to a certain set of parameters. So now let us say that the control input, this control input here, is dependent on the information residing in all the states of the plant, xk. Then you say it is a full state feedback law, as generally expressed this fashion. uk is a control input, is given as minus k xk, where k here is the gain matrix or the gain set of gains, and xk is the state vector. So the information in the state vector multiplied by a set of gains is what is going to give you the control input for this particular plant. So this is called the control law, or the full state feedback control law for the system. So let us see how this comes about. So let us take the feedback. This is the sensed output, and what is it that you are going to feedback? You are going to feedback all the states of the system. So state vector you are going to feedback, and there is going to be a comparator where you compare with the reference, and then you have an error, and that error goes into the controller. A controller here is a set of gains k, and that is the output of the controller is given as the input to the plant. So now let us mark the variables. So this is xk, the state vector, which is comprised of two parts. One is the steady state value x, which relates to the nominal operating point, and this other part is the deviations in the neighborhood of the nominal operating point. These are small deviations, xk hat. Now this is compared with the reference. The reference is basically the nominal steady state operating point value. So these two are compared, and what you get here is minus xk hat, only the difference relating to the difference in the deviations about x, uppercase x. Now this gets multiplied by k, and you have the xk hat. So that is the control input. But we also have feed forward aspect which will come in, as I say. So let us say this is nx, another fixed matrix, and what is its job? From a known set of reference value. For example, if I am doing speed control of a motor, so what is fed back? So if I take a DC motor, we have seen that there are two states. One is the angular speed, and the other one is armature current IA. So let us say we are feeding back IA and the angular speed. This is x. But what we wish to control here, the reference is, let us say, the speed of the motor. So omega reference will be there. But the x here should have the reference for both the states, in this case IA and omega. So the job of this nx matrix here is to convert the fixed reference of the speed to the nominal operating point IA omega, and that is what will be used for comparing with the state vector. So that is the job of nx. So from this fixed reference, we shall also give a feed forward point here. Now when you give the feed forward point here, this is nominal operating point u, and what is coming out of the controller k is minus k xk hat, that is uk hat, the small signal input, deviations about the nominal operating point. So if you look at this part here, the controller k, xk hat and then uk hat, you see that this follows the control law. This is the state feedback control law that we are using for the small signal deviations, where k is the controller. Now we shall obtain u from this reference input. So a reference input r is used not only for obtaining the nominal operating point state vector here as the reference, it is also used to pass through another matrix nu to convert it into a nominal value input value for the control input. So generate the nominal input value. This will be added with the controller output, which will give the deviation in the neighborhood of u, and that will get summed up and then go as the total control input to the plant. So this is the total structure of a full state feedback control system. What is our job? We need to design the value of k, we need to design the value of nx, we need to design the value of nu. These three matrices or these three blocks we need to design in order to get the full state feedback control system. Let's see how we go about doing that. To design k, nx and nu, let us start from the state space model of the plant. So let us write that down. xk plus 1 is equal to xk plus buk. So this is the state equation in the discrete domain. Now, rewritten that state equation and replaced uk with the nominal operating point value plus the deviation in the neighborhood of the nominal operating point uk hat. So uk can be replaced by u plus uk hat. Likewise, you do the same for xk as x, uppercase x, which represents the nominal operating point, plus xk hat, deviation about the nominal operating point. And the same with xk plus 1 at the k plus 1th instant. It is again x. There is no change in the nominal operating point value with time, plus xk plus 1 hat. In this equation, I have done one more change. I have replaced uk hat using the control law minus kxk hat. I have replaced uk with minus kxk hat. Recall that the controller output is the input, which is minus xk hat into k, which will be the small signal value of the control input, which will go, which is basically the controller output. So this is the control law, and this is what we would like to replace in that equation. So now let us separate this equation into two parts. One is the nominal operating point value part, that is the steady state value part, the uppercase values, and the small signal part, the deviations in the neighborhood of the nominal operating point part. So this is the small signal part. So this varies with time, the small signal part, and therefore you have xk plus 1 hat is equal to axk minus b k x k hat. So this will be the small signal equation. So remember this, x k plus 1 hat can be written as a minus b k x k hat. So this is one equation that we can mark it as equation number 1. We need that to derive the design equation for nx, nu and k. So if k tends to infinity, so as time progresses, so we would like the deviations in the neighborhood of the operating point to ultimately go to 0, and finally the values will tend to these uppercase values. So as k tends to infinity, xk hat will tend to 0, the deviations tend to 0, and what will be left off in this equation, in this original state equation here, is only the steady state value or the nominal operating point values. So you will have it as x, which is ax plus bu. So now you can rewrite this, putting these two together as A minus I identity matrix x plus bu is equal to a null vector. Now I can make a replacement for x as nx r and for u as nu r. How did I get this? Let us go back to the block diagram. So you see here, what is this steady state value or the nominal operating point value? X is equal to, it is r into nx. Okay. And what is this nominal operating point input? U equal to, it is again r into nu. So this is what we are replacing there. So remember this equation. So this is also another equation. We will give it a number 2. So this is the second equation that you need to remember. This is equation 1 and this is equation 2. So these two equations are coming out of the state equation. Xk plus 1 is equal to xk plus buk. Now let us look at the output equation and see what we can get, what information we can get out of that. Let us consider the output equation. Yk equals cxk plus duk. As before, let us express the time variables yk, xk and duk in terms of two parts, one being the nominal value, operating point value, and the other being the deviations in the neighborhood of the nominal operating value. So if you rewrite that, you see that yk gets expressed as the nominal operating point value uppercase Y plus deviations about the nominal operating point. Likewise, x can be expressed as uppercase X, which represents the nominal operating point, and xk had deviations about the nominal operating point. Likewise for uk, which is composed of uppercase U and the deviation value uk hat. Normally the term duk is representing a feed through term. So you have a dynamical system, and if you are having a feed through term which directly goes from the input to the output bypassing the dynamical system, then you can remove this duk term and concentrate on the dynamical part, which is y is equal to cxk for closed loop operation. For closed looping, you can consider y is equal to cxk without loss of generality. So let us take that part which is leading to the dynamics of the system, dynamics of the state values and the output values, which can be used for feeding back. Y is the controlled output, and this is what you want to feed back, which means that this is what you want to control to some specific value, which means that you would like to set a reference for this particular controlled output variable. So in the example that we discussed, In the case of a DC motor control, you have two state vectors IA and omega. So let's say you want to control omega, then omega becomes Y. Omega becomes the controlled output, and you would like to set the reference for omega. So that Y approaches or becomes same as the reference value with zero error. So in the steady state, Y will reach R, and this equation R plus YK hat, which is equal to Cx plus Xk hat, can be still further rewritten. If you take it to steady state, when large amount of time has elapsed, k is tending to infinity, then we know that xk hat tends towards 0, and if xk hat tends towards 0, yk hat also tends towards 0. So what remains is R equals Cx, and x we know we can write in terms of the reference as nx into R. So this is the equation that we can obtain provided under the condition that the time has elapsed, k tends to infinity, and as a consequence the deviation about the nominal operating point will tend to 0. So this can happen if Cnx is equal to identity matrix. So let us give this a number 3. Remember this also, Cnx is equal to I, identity matrix. So using these three equations, we should be able to design our controller, full state feedback controller. So let us see how we can use these design equations. So the first equation that we obtained, which we wanted to remember, is the small signal dynamic equation, state equation. Xk plus 1 hat is equal to A minus Bk Xk hat. A minus Bk is now the characteristic matrix for this small signal dynamical equation, which is now under closed loop. This A minus Bk, the roots of the characteristic equation of this A minus Bk are actually the poles of the closed loop system, and they must lie within the unit circle. If they all lie within the unit circle, then we know that this is a stable system, that xk hat will decay ultimately to 0. So A minus Bk is the one that will be used for obtaining the controller gains k. So normally A and B are obtained from the model of the system by way of modeling the dynamical plant. The roots of the characteristic equation of A minus Bk are the poles of the closed loop system, which are placed by the designer. You place the poles within the unit circle in an appropriate manner, and you have the values of the closed loop pole locations. And using that, using the value of A, using the value of B, k is the only unknown that can be calculated in a closed form way. The second equation that we had written down, A minus I nxr plus B nur is equal to a null vector. Third equation we saw from the output equation, we got this Cnx is equal to I, identity. So this second and third equation, you can combine them into a matrix equation using nx and nu as the focal variables. So using nx and nu as the focal variable, A minus A nx plus B nu C nx, nu doesn't play a role here, they are equal to a null vector and the identity vector. So here if you see in this equation, A is known, B is known, C is known, I is an identity vector, this is a null vector. Likewise on the right hand side you have null and identity vector. Nx and nu are the only unknowns, therefore they can be calculated in a closed form way. So using these equations 1, 2 and 3, you can in a closed form way calculate what should be the controller gain K, Nx matrix and Nu matrix. So this can be done for any given system, any given state space system which is modeled as xk plus 1 is equal to ax plus bu, yk is equal to cx. So all the systems modelable in this fashion can be designed for this full state feedback control. So let us clarify later with some examples which will make it clear how we design the values of k, nx and nu.